While hiking in nature, in many parts of the world, it's easy to notice ordinary rocks. Dull, colorless, with nothing that really catches your eye. But did you know that in some places, those same ordinary stones can actually signal the presence of mineral deposits worth millions of dollars? These are the kind of rocks anyone would kick aside on a trail without a second thought. And yet, what almost nobody realizes is that these ugly rocks are the silent foundation of the most expensive technologies on the planet. Without the minerals they contain, there would be no smartphones, no electric cars, no solar panels, no satellites in orbit. And you wouldn't even be watching this video right now. That's why discovering a deposit with these minerals can literally turn a property owner into a millionaire, depending on the size and concentration of what's found. In other words, behind every iPhone, Tesla, or computer chip, there's an ordinary-looking rock hiding strategic minerals. These are the elements driving the global economy, and they're becoming increasingly valuable. Governments, corporations, and investors are locked in a worldwide race to secure new sources of these rocks. While most people walk right past them without noticing, geologists and prospectors know that a single hillside can be worth more than an entire building. And here's the part that surprises most people. These rocks aren't hidden on distant planets or in secret underground mines. They're right here on Earth, all around us. In the mountains you drive through, in road cuts along highways, in construction zones, and even in quiet rural areas that look completely ordinary. If you live near volcanic regions, mountain ranges, or areas with granite and pegmatite outcrops, chances are you're surrounded by the same materials used in technologies worth billions of dollars. But how can something so dull and colorless be worth that much? That's exactly what we're going to uncover today. The three rocks you're about to see don't sparkle or stand out, but without them, modern technology simply couldn't exist. So pay close attention, because after this video, every walk in nature might turn into a real treasure hunt. And if you enjoy what you're about to see, don't forget to subscribe to the channel so you can learn how to identify other valuable minerals in nature, like diamonds and sapphires. Have you ever wondered how an electric car can cost over $100,000? Or why high-end smartphones have become so expensive in recent years? The answer, in large part, comes down to a single element: lithium. It's the heart of modern batteries. And what most people don't realize is that it all starts with fragments of dull, whitish rocks scattered across the ground in places that look completely ordinary. To turn these stones into cutting-edge technology, the process begins deep in nature. Lithium isn't mined as a pure metal. It appears in specific minerals, mainly spodumene and lepidolite, found in rocks called pegmatites, a type of granite that cools slowly, allowing valuable crystals to grow. These rocks are collected, crushed, and processed to separate the lithium-bearing minerals. Then the material goes through a chemical treatment to extract lithium carbonate or lithium hydroxide, which are the compounds used to produce lithium-ion batteries. In other words, a journey that begins with a dull rock ends up powering satellites, laptops, drones, and high-precision military systems. Today, lithium is known as the white gold of the 21st century. Without it, there would be no clean energy transition. That's why global demand is skyrocketing. Just to give you an idea, a single electric vehicle can contain up to 22 pounds of lithium in its battery pack, and a home backup battery can hold even more. Most of the world's reserves are concentrated in the so-called lithium triangle, formed by Chile, Bolivia, and Argentina. But the United States also has important deposits, especially in Nevada, North Carolina, and California, while Australia leads global production from its vast pegmatite fields. Now for the practical part. How can you identify signs of lithium in nature? The first step is to look at the rock type. Lithium is usually found in light-colored pegmatites, often whitish or pinkish, with visible crystals of quartz, feldspar, and mica. Spodumene, the main lithium-bearing mineral, appears as long, prismatic crystals with shades ranging from white and pale green to lilac. The lilac variety is known as kunzite, and it's actually used as a gemstone. Lepidolite, another lithium-rich mineral, has a pearly luster and comes in pink, purple, or silvery gray tones. It breaks easily into thin sheets and often occurs alongside tourmaline and other minerals in pegmatitic veins. So if you come across a light-colored rock packed with these kinds of crystals in an area known for granite or pegmatite outcrops, it's time to take a closer look. And lithium isn't found only in rocks. In some regions, it also occurs in clay formations rich in lithium or dissolved in underground brines, especially in arid zones with ancient evaporated lakes. In those cases, geologists test soil, groundwater, and surface crust samples, searching for unusual concentrations of lithium. But here's the key. Even if a rock looks ordinary, the clues can be there. A tiny fragment of spodumene might point to a much larger deposit hidden below. That's exactly what prospectors and mining companies are looking for. Subtle signs in places most people overlook. So think about it. If you're hiking through an area with pale granite outcrops and you notice faintly colored glassy crystals on the ground, could you be walking right over a lithium deposit? If lithium is the heart of modern batteries, cobalt is the muscle that makes them last. Without it, stored energy would degrade much faster, and electric vehicles wouldn't last nearly as long. This blue, dense, and discrete metal is essential for boosting the efficiency and durability of rechargeable batteries, especially those used in EVs, wind turbines, and portable electronics. Beyond that, cobalt is also critical in high-temperature alloys used in jet engines, aircraft turbines, and precision medical instruments. But here's the problem. Over 70% of the world's cobalt supply comes from the Democratic Republic of Congo, a country where unsafe working conditions and armed conflict have turned this metal into one of the most controversial raw materials. That's why there's now a global race to find new, ethical, and secure deposits, especially in the United States, Canada, and Australia. And this is where geological knowledge becomes a real opportunity. Cobalt rarely occurs alone in nature. It's typically found alongside copper and nickel in igneous and metamorphic rocks. The main host rocks include gabbros, altered basalts, schists, and serpentinites, often rich in magnetite and pyrrhotite, two dark metallic minerals that can indicate the presence of cobalt. The most recognizable cobalt minerals include cobaltite, CoSS, which has a gray metallic color with reddish reflections, and sphero-cobaltite, CoCO3, which can appear in pinkish hues. In many cases, cobalt shows up as trace elements within copper or nickel minerals, which makes field identification harder and requires careful attention to surrounding minerals. If you want to recognize an area with cobalt potential, look for dense, dark-colored rocks, especially where there are signs of hydrothermal alteration, like colorful oxide stains, quartz veins containing metallic sulfides, or fragments with a bluish metallic shine. In mountainous regions or old volcanic zones, fragments of green schist, amphibolite, and serpentinite may also carry traces of cobalt. In the United States, the most promising deposits are found in Idaho, Montana, Missouri, and Minnesota, where cobalt is associated with formations rich in copper and nickel. In these areas, the soil might contain small, bluish-gray, metallic fragments with a strong luster under sunlight, one of the early signs of mineral alteration. Another key detail, cobalt often occurs in the same geological structures as high-value gemstones, such as garnets, tourmalines, and beryls, especially in metamorphic zones with intense hydrothermal activity. That means in some locations, the hunt for precious stones and critical metals might overlap, something experienced geologists and mineral hunters always keep an eye on. And when a deposit is confirmed, the numbers can be staggering. A medium-sized cobalt mine can generate $20 to $40 million per year, depending on ore purity and market value. For large-scale operations, one like those being developed in Idaho, projections exceed $100 million annually. Even a small find on private land, if economically viable, could be worth a fortune in mining rights. So just imagine. A dark, ordinary-looking rock found on a remote hillside in rural America might be the first clue to a deposit that could supply part of the nation's battery industry. And it all starts with someone who knows how to read what the ground is saying. That's why if you spot dark, metallic rocks with a bluish shine and nearby quartz veins, don't dismiss them. It might look like just another rock, or it could be the beginning of a discovery that puts your name among the new owners of the metal, fueling the future of clean energy. Although it's one of the most common minerals on Earth, quartz is also one of the most important stones for modern technology. It's in almost everything we use daily, from watches and computers to satellites and solar panels. And the reason is simple: piezoelectricity, the ability of quartz to generate a tiny electrical charge when compressed or placed under pressure. That's what allows quartz to function as a natural oscillator, keeping time accurately, converting vibrations into electrical signals, and helping synchronize all kinds of electronic equipment. So every time you check the time on a digital watch or use GPS on your phone, chances are a tiny quartz crystal is working silently inside the device. But quartz's importance goes far beyond consumer electronics. It's also the main raw material for the optics and semiconductor industries, because silicon, the key element used to make microchips, is obtained from silica-rich rocks like quartz. The process starts with the melting of high-purity quartz crystals, which are heated to extremely high temperatures until they become metallic silicon. That silicon is then refined and recrystallized into what we call semiconductor wafers, thin slices of material that form the base of all the microchips on the planet. In other words, quartz is the starting point of all modern computing. Without it, there would be no computers, smartphones, or even the internet. In nature, quartz can take many forms. In some areas, it appears as large transparent crystals, shining from rock crevices. In others, it shows up as milky or opaque masses, white or gray, forming massive blocks. The purest varieties usually form in hydrothermal veins, fissures in granite where hot water rich in silica has circulated. As this silica cools and deposits slowly, perfect crystals can grow, resulting in translucent quartz of high industrial quality. It's also common in quartzites and recrystallized sandstones, where heat and pressure have transformed ancient sandy sediments into nearly pure blocks of quartz. In the United States, there are regions world-famous for both the abundance and quality of quartz crystals. One of the most well-known is Arkansas, particularly the Mount Ida area, known as the quartz capital of the world. There, crystals grow in underground cavities within sandstone and schist, forming transparent prisms that can reach several inches in length. Another important region is Colorado, where quartz is found in pegmatites and granite veins in the Rocky Mountains, often alongside feldspar and mica. In North Carolina, you'll find beautiful specimens of milky quartz and even amethyst, especially in secondary deposits carried by rivers and alluvial soils. Finding quartz in nature is easier than you might think. Just pay close attention to light-colored, shiny rocks along trails, hillsides, and riverbanks. The crystals often have smooth, pointed surfaces, sometimes grouped in hexagonal formations that reflect sunlight in a distinct way. In areas with historical mining activity, broken quartz fragments often glimmer among the more ordinary stones, giving away their presence. And the rule is simple: the more translucent and impurity-free the crystal, the greater its potential value to industry. It's almost ironic that something so common is also so essential. Quartz is a stone that bridges the natural and the digital worlds, an ancient mineral at the core of today's most advanced technologies. Without these seemingly simple and transparent stones, no screens, no chips, no solar panels would exist. They are the silent heart of our time, pulsing inside every device we use. Invisible, but absolutely indispensable. Among all the strategic materials used in modern technology, diamonds are still unmatched. They remain the hardest natural substance known and the best thermal conductor ever discovered. These properties make diamonds essential for industrial lasers, precision cutting tools, high-performance drill bits, and the next generation of semiconductors. In recent years, lab-grown diamonds with ultra-high purity have started to revolutionize microelectronics and quantum computing, gradually replacing silicon in certain components thanks to their ability to dissipate heat and conduct energy with minimal loss. In other words, the same crystal that shines in fine jewelry might soon become the foundation for superprocessors and cutting-edge medical technologies. But to understand how diamonds are found in nature, you have to look deep underground, literally. Natural diamonds form more than 90 miles, 150 kilometers, below the Earth's surface, in areas of the mantle where both pressure and temperature reach extreme levels. Millions of years ago, during ancient volcanic eruptions, these diamonds were carried toward the surface by special types of rocks called kimberlites and lamproites, geological chimneys that pierce through the Earth's crust and bring the crystals up from the deep. These are the formations where miners and geologists focus their search. Finding these rocks becomes easier with the help of what are called indicator minerals, small geological clues that signal the potential presence of diamonds nearby. Some of the most important indicators include pyrope garnet, ilmenite, chromite spinel, and olivine. These minerals form under the same high-pressure conditions as diamonds and are durable enough to survive the long journey to the surface, making them excellent markers for locating kimberlite pipes. In practical terms, when a prospector spots reddish pyrope garnets, green olivine, or black ilmenite crystals in river gravel, that's a strong sign that a diamond-bearing source might be nearby. In the United States, there are well-known sites where these geological clues lead to real discoveries. The most famous is the Crater of Diamonds State Park in Arkansas, where anyone can search for diamonds and even keep what they find. The ground there is part of an ancient kimberlite pipe, the same type of rock that produced legendary diamond mines in Africa and Siberia. Beyond Arkansas, diamonds have also been found in Colorado, Montana, and Wyoming, especially in regions rich in kimberlites and related alluvial deposits, areas where diamonds have been carried away by erosion over thousands of years and mixed into riverbeds and sediment layers. In nature, raw diamonds rarely look like the sparkling gems you see in jewelry stores. They're usually translucent, milky white, or yellowish, with irregular surfaces and a greasy texture. In alluvial deposits, they hide among ordinary pebbles but can often be identified by their internal luster and unusual weight. When you hold a small diamond crystal, it feels noticeably heavier than a typical stone of the same size. Inside kimberlite rock, diamonds appear embedded in a dark, compact matrix, often alongside indicator minerals scattered throughout the rock. Knowing how to recognize these signs is what separates a casual rock collector from a true diamond hunter. Finding even a single natural crystal can change someone's life. And what's most fascinating is that behind every diamond is a story written over billions of years, forged in the deepest layers of the earth, and revealed only to those who know how to look. But before you rush out to start searching for rocks that could be worth a fortune, there's one last thing you need to know. A lot of people out there do find stones with serious value, but because they don't know how to properly identify the mineral type, they either ignore it or worse, sell it for a fraction of what it's really worth. Unfortunately, this happens all the time. Valuable minerals and even gemstones being sold for ridiculous prices simply because the person holding them didn't recognize what they had. That's exactly why I created the book, Gemology Journey for Beginners, a complete, straightforward, and practical guide made for anyone who wants to learn how to identify the most common types of rocks and minerals, even without professional tools. Inside, you'll learn how to perform simple tests for hardness, density, texture, and luster using everyday tools. And if your goal isn't to sell, no problem. The book also includes an exclusive collector's chart listing some of the world's most valuable minerals, their characteristics, rarity levels, and practical tips to organize your finds as your collection grows. Now, if you're still taking your first steps or just not ready to grab the book yet, that's perfectly fine. You can subscribe for free right here on the channel and keep following our videos, like the one already showing up on your screen, to keep learning how to identify rocks with critical metals, which are now the new gold of the tech industry. Thanks for liking and subscribing. Good luck, Gem Hunter.